Okay, in this video, we're going to be talking about calculating the force of gravity between two objects. So we've talked about calculating the force of gravity at sea level between an object and the Earth. However, that is actually a simplification of a formula that we use to calculate the force of gravity between two objects. So let's do that here. I've got the formula here is going to be the force is equal to the gravitational constant multiplied by a ratio of the mass of the first object times the mass of the second object divided by the square of the distance between the two objects. Okay, that does sound like a lot, but I'll break it down for you. First of all, I said something rather new. I haven't shown you an equation yet with a constant in it. And a constant just means that for every single time you use this equation, this letter here, big G, is going to be the same thing. We all live in the same universe. Gravity interacts with things with the exact same ratio of force. So for this class, it's a little bit more precise than this, but for this class, our gravitational constant is going to be 6.67 times 10 to the negative 11 Newton meters squared over kilogram squared. Now that looks like a lot, but really all you need to know is the 6.67 times 10 to the negative 11 as far as the number, and that's a very small number if you know your scientific notation. There's a lot of zeros in front of this 6. So that tells you that gravity isn't a particularly strong force on its own. You either need to have a lot of mass or be really close together to feel the force of gravity. So let's see. Say I was floating in space next to my friend, or even not floating in space. Say I was just standing 1 meter apart from my friend. What is the force that we are acting upon each other? So let me keep the formula and frame here. So I've got the force of gravity that we're trying to calculate is going to be equal to big G. So let me put it in parentheses here. 6.67 10 to the negative 11th. I'm going to leave off all of my, I know I always tell you to put the units, but I'm going to leave off all my units just because it's a lot to write, and it's going to cancel out the units that we're going to write with our masses, my kilograms, because that'll be on the top, see? So I'll have kilograms times kilograms on the top, making kilograms squared. It's going to cancel that out. And then I'm going to have meters squared on the bottom because I'm going to have the distance we are apart squared on the bottom, leaving us with newtons, which would be the force. Anyway, so on to the ratio. So I am 75 kilograms, at least in this example. I don't know exactly what I am right now. And then my friend is 65 kilograms. All right, cool. And then we are 1 meter apart. So 1 squared is still 1 and meters squared. So if we were 2 meters apart, then it would be divided by 4 meters squared. If we were 3 meters apart, it would be 9 meters squared. So you kind of see how this inverse square law is usually what this is. This kind of phenomenon is called, how gravity is going to start reducing really fast if I've got more and more distance in my denominator here. All right, so let's go ahead and calculate this out. Let's simplify this a little bit. Let's go step by step. Luckily, it's divided by 1, so I can kind of just take this out since my meters are going to be canceled out with my meters and my gravitational constant. And then I've got just 75 times 65. And then I've got 75 kilograms. Oh, excuse me. 4,875 kilograms squared times my gravitational constant. And I'm going to go ahead and write my units that are left. My meters have been canceled out, but I will have 6.67 times 10 to the negative 11 newtons over kilograms squared. And since that's in the denominator, this is in the numerator, this is like imaginarily over 1 here. I can cancel out my kilograms squared, left with newtons, and that should give me my force. All right, so 4,875 times this really tiny number. Remember, it's multiplied by 10 to the negative 11th. So let me type that into my calculator really quick. So 6.67 times 10 to the negative 11th. Is going to give me yet another really, really small number. So my answer for forces here is going to be 3 point, what significant figures do I start with? Just 2. So let me just round to 3.3 times 10 to the negative 7 newtons. Or if I take this out of scientific notation, let me do 1, 2, 3, 4, 5, 6, 7 zeros. So 0.0000033, which is really, really small. So this is why we really can't feel the force of gravity between us and a friend in a room. It does exist. This number is calculable, but it's very hard to measure, even with the most precise instrumentation. And we absolutely cannot feel it. But this is how we use the law of universal gravitation and put it into practice and calculate the force of gravity. And as you can imagine, unless an object is really, really massive, like the Earth, or it's very, very close, we really don't have that much force going on between objects.